In this video, we are going to discuss mean value theorems and some other applications of derivatives. So first of all, let me discuss the definition of local maximum and local minimum. Let's say we have a function that goes from a metric space X into the reals. Okay, X, a general metric space. And we will say that F has a local maximum at a given point P in X if there is a neighborhood that exists delta positive such that the function is it's smaller everywhere around that point P. Okay, so we have f of q less or equal than f of p for all q in X that is within a neighborhood of radius delta from P. So dP, the distance from P to Q, less than delta. And similarly, we can define a local minimum if the function is bigger or equal around the point P that we were discussing in a neighborhood. Now, one thing that I want to emphasize here is that these are open neighborhoods. Okay, you see, these are open neighborhoods. So somehow this is a typical confusion. If we have a function like this, clearly it has a local maximum. Okay, because it's an interior point and around P the function is smaller. But if we have a function like this, okay, this would not be a local maximum according to the definition. Okay, notice that in the definition we are asking an open neighborhood around the point. Okay, in this case, because we are at an endpoint of the interval, it's kind of left out. But this you will see in other books that it may be defined differently. So just pay attention to the context whenever if you need a maximum node at the boundary point. Okay, anyway. The most important thing about maxima and minima is this result, this theorem from Calculus 1 that allows us to characterize this extrema when the function is differentiable. So let's say that we have a function f from a closed interval ab, a real function. Then if f has a local maximum or minimum at the point C inside the interval, in the open interval, and if f prime of C exists, then f prime of C must be 0. Okay, so what this means this is a necessary condition. This means that in order to locate the critical values, okay, the points where there could be a maximum or a minimum, we need to check the points where f prime of c is 0 or f prime does not exist. Okay, so those are the points where we need to search. And actually, this is very convenient because suddenly these are just a few points. Okay, so it tells you where to look for extreme. Now the proof, let's discuss it. Here, so we have our AB, and here we are going to, you see, to take C, the C in the statement. Okay, and because it's inside, we can take a neighborhood around, which would be, would be C plus delta, C minus delta. Okay, this is the neighborhood in the definition of local maximum. Okay, you see that it says that there is a neighborhood of radius delta around it. So that's the one we are considering here. Okay, so if you want to be more formal, what I'm saying is that we need to be able to put C minus delta in between C and A and C plus delta in between C and B. It's the same thing. Okay. So here now we are going to take points, okay, that we are going to be working on this side on the left of C. Okay, we are going to take points. Let me continue with the color code. So C minus delta less than T less than C. Okay, we are going to take T here. In this case, okay, because we know it's a local maximum, at C, that means that f of t minus f of x is going to be less or equal than 0, okay, for every t around C. But now, what I'm going to do, I'm going to divide ft minus fc, I'm going to divide it by t minus c. Okay, but notice that t minus c is negative. Okay, so then it's going to switch to flip the inequality. Okay, so now we have the quotient that we need for the definition of derivatives, so we can let t converse to c from the left. And we get that the derivative at C must be non-negative. Okay, remember we are assuming that the derivative exists. Okay, so this one-sided limit actually equals the full limit that is the derivative. The important thing here is this piece of information that the derivative is non-negative. Because now we can take here, we can take our t on the right of c. Okay, so now we are going to have t in between c and c plus delta. And we can basically repeat what we just did. Okay, because f is a local maximum, f of t minus f of c is less or equal than 0. But now because t minus c is positive, I can just divide by it. Okay, and I get, taking limits, as t converges to c from the right, f of t minus f of c divided by t minus c less or equal than 0. That means that f prime of c is less or equal than 0. Okay, again here, we already knew that the derivative existed. The piece of information that we are getting is that it must be non-positive. Okay, but then putting together both pieces of information, okay, what we get is that f prime of c must be equal to 0. That's the only option that is left, which is what this is what we wanted to prove. So we are done here. From this result, we can prove what is called Rolle's theorem. Okay, and what does Rolle's theorem say? So whenever we have a function from a closed interval, a real function that is continuous, okay, is continuous in the closed interval, but also differentiable in the open interval, okay, then what the theorem says is that there exists, sorry, I'm forgetting one more thing. So we need f continuous, differentiable, and f of a equal to f of b. That's the third hypothesis in Rolle's theorem. Then, now is the good one, there exists a constant c in the open interval such that f prime of c equals 0. Okay, this is a very well-known result from calculus, but it's very useful nevertheless. So here we have our AB, and we have that f at A equals f at B, and the function is continuous and differentiable. There is no way around it. Anyway, you try to do a picture, at some point the slope will be horizontal. Okay, and horizontal slopes will give us horizontal tangents. Okay, and that means the derivative equal to 0. But I'm getting a little ahead of myself. So let's prove Rolle's theorem first, and then go from there. So proof. So here we are going to use the extreme value theorem that we saw for continuous functions. Okay, here we are using that f is continuous. This is saying that f has a maximum in the closed interval AB. Okay, here it's very important that we are working on a compact set, AB. Okay. So let me actually emphasize that f continues in the closed interval. But then we can apply the extreme value theorem to negative f, okay, and then get that f has a minimum in AB. Okay, so it has to have both a maximum and a minimum. Now, if the maximum and the minimum both happen on the boundary, on the endpoints, okay, A and B, then what happens? Then the function must be constant. Okay, because by hypothesis, we have that f of A equals f of B, and then it would be equal to the maximum and minimum in AB. Okay, and what happens now? If f is constant, then what is the derivative? It's 0. Okay, so then we are good, because that means for all the points in AB, the derivative is 0. So that means that in particular there is some point. Okay, but now the other possibility is that either it has a local maximum or a local minimum in the interior. Okay, and if that happens, we have seen by the previous theorem let's say, well, the derivative at that local maximum or minimum must be equal to 0. Okay, and then this is also what we wanted to prove. So in this case, we are also able to finish the proof. All right. So either way, we are able to finish the proof of Rolle's theorem. And then there are some generalizations of Rolle's theorem. The first one is the mean value theorem. Okay, here what we are saying is that we have a function that is continuous in the closed interval AB and differentiable in the open interval. Okay, and then the theorem says that there exists C in the open interval AB such that f of B minus f of A equals B minus A times f prime of C. And that is the mean value theorem. Again, this has a geometric interpretation. Okay, let's say this is A, this is B. And this is my function f. Okay, so here, let me use colors. Here we have our second line. Okay, and what is the slope of the second? Well, it's this difference divided by the difference in x. Okay, so it will be f of b minus f of a divided by b minus a. And what the theorem is saying is that there is some point, okay, let's say that I produce a copy of this line and then I move it around up and down. You see what happened there? There is a point in the interval such that the slope of the tangent is precisely the same. And that point is c in the theorem, okay? And then f prime of c equals the slope of the tangent. So that is what the theorem is saying. In particular, of course, if f of b equals f of a, we fall back to Rolle's theorem. Okay, so this is more general. And actually, we can prove it using Rolle's theorem. But instead of proving this theorem, I'm going to show a generalized mean value theorem. Sometimes it's called Cauchy's mean value theorem. Okay, so what does this one say? For this one, we have two continuous functions. Continuous in the closed interval, and both of them differentiable in the open interval. Okay. Now, what the theorem says is that then there is a point, there exists C in the open interval such that f of b minus f of a times g prime of c equals g of b minus g of a times f prime of c. Okay, now one note. The generalized mean value theorem implies the mean value theorem. We just need to take g of x equals to the identity, okay, equal to x. And then we fall back to the mean value theorem. So we will prove the generalized mean value theorem. Okay, but this one is very easy actually. Once we have proved Rolle's theorem, the job is basically done. So here we are going to define, so the trick, Rolle's theorem works for one function, one real function. So we are going to transform this condition we have here into something that involves only one function. Okay, so what I'm going to define is f of b minus f of a times g of t, okay, minus g of b minus g of a times f of t. And here, of course, t is in between a and b. I define this function because if you notice here, where the derivatives are, okay, it's kind of asking for it. Now, one more thing that we need to notice is that h of a equals f of b minus f of a times g of a minus g of b minus g of a times f of a. Okay, and then here we can do the cross products, but we see fbga minus fага minus gbfa plus gafa, and there is a cancellation. Okay, you saw that? But then if I compute h of b, on this part you check, I get exactly the same. Okay, so we are in the conditions of Rolle's theorem because h is continuous in AB because f and g are. It's differentiable in AB, and h of A equals h of B. So then Rolle's theorem implies that there exists C in AB such that h prime of C equals 0. Okay, and this is the C in the generalized mean value theorem. Okay, and here we are done because h prime of C equals 0 is equivalent to the conclusion of the theorem, which is this one over here that I'm going to copy paste. Okay, and then we are done. Again, if we want to do the proof, suppose you want to do the proof of the mean value theorem, but not the generalized one. So you can follow this proof, putting G equal the identity every time. Finally, I want to mention one conclusion of the mean value theorem. If we have a differentiable function, differentiable in AB, the open interval, therefore also continuous. And we know that f prime is non-negative, okay, for all x in the open interval. Then f is monotonically increasing. Let me bring this over here. Monotonically increasing. Okay. If it happens to be identically 0 everywhere, then f is constant. Notice that we have used the converse. We used that if f is constant, then the derivative is 0. But here we are saying the opposite, that if you know it's everywhere 0, the derivative, then the function must be constant. And then the last is that if we have a non-positive derivative everywhere in the interval, then f is monotonically decreasing. Okay, interpretation here is clear in terms of tangents. Okay, when we have a tangent that is positive, then the function is increasing. If we have a tangent that is negative, then the function is decreasing. Okay, but for proof, actually we use the mean value theorem. Okay, the proof is very easy. Just take a pair of numbers, x1, x2, in the open interval, and then the mean value theorem is going to tell us that f of x2 minus f of x1 equals x2 minus x1 times f prime of c for some c in x1, x2. Okay, but here that's it. Okay, because let's say this is a subset of AB. Let's say that we want to prove B. Okay, B is saying that if f prime is equal to 0 everywhere in the open interval, then f is constant. So to show B, basically notice that f prime of c must be 0 because it's 0 everywhere. Okay, and that means that f of x2 equals f of x1, looking at this equation. Okay, and if that is the case for every pair of points x1, x2, that's it. It must be constant. But also, this shows A, because if f prime of c is non-negative, then f of x2 minus f of x1 must be non-negative. Okay, and that means that the function is increasing. Yes, there's a little thing here. So we have x2 minus x1, right, times f prime of c. So I need both of them to be positive. Okay, so then positive for x2 bigger or equal than x1. So we have proved the monotonicity. Okay, we are saying that if x1 less or equal than x2, then f of x1 less or equal than f of x2. And the last case is similar.